All right, hello everybody. Welcome to our guest speaker event. Before we get started, I'm going to spend a few minutes or a few seconds talking about our organization for those of you who aren't familiar with us. I know for me, I see a lot of new faces or new names here that we haven't seen before at our previous events. So for those of you who are new, welcome. And for those of you who are returning, welcome back. So we are the Young Expressionists, TYE, a nonprofit organization founded in 2020 with the mission to share skills and inspire others. So we mainly just host a variety of classes, both online and in person, along with other events such as the one that you guys are attending right now. So if you're interested in subscribing to our guest speaker mailing list to be updated on future events, be sure to drop your email in the form linked in the chat. I believe Jacqueline just sent the form into the chat. You can also learn more about us at our website at theyoungexpressionist.org. So Jack probably already sent that one in the chat as well. So that's about it. So I'm just going to turn it over to Jacqueline now to introduce our guest speaker for today.
Yeah, so our speaker today is Anton Lawrendra. Anton graduated from Valley Christian High School in 2009. Some of us here might be Valley students. Emma and I are from Valley Christian High School. And he's now working as a hardware engineer designing chips for Tesla's self-driving AI supercomputer program. And he just has lots of experience working in chip design in various different companies. So today, during this webinar, he'll be sharing his experience, his background, and kind of his journey to becoming a chip designer, and also why computer chips are so important. And we will have time for you guys to ask questions at the end, so please hold off until then with your questions. And now I'll hand it over to Anton.
Thanks, Emma. Thanks, Jacqueline. Let me start sharing my slides. Okay, let me make this. Can you guys see my presentation?
Yeah.
Okay, cool. So yeah, let's get started. So, thanks again, Emma and Jacqueline, for having me here today. So just to break the ice a little bit, to give a little bit of background about myself. So I grew up in San Jose, California, like heart of Silicon Valley. And yeah, I got married in 2016 and been married for 6 years now. I moved to Hayward, East Bay, not too far from San Jose, in 2018. So we've been living there for 4 years now. I have 2 boys now. On the left is Ezekiel. He's 3 years old. He goes by Zeke, and the younger one on the right is Ezra. He's turning 2 in April. People may be wondering, based on my name, like what ethnicity is he, right? So ethnically, I'm Chinese, but my family is from Indonesia. My wife's family is also from Indonesia. And yeah, some hobbies I have, just like jogging, playing basketball, and playing piano whenever I get some spare time. So yeah, so like Jacqueline already mentioned, I'm going to be going over like my journey, like all the way from like even elementary school, all the way through high school, college, and kind of some of the work experiences I've had. I'll start with that and then go a little bit more into like specifics into like the kinds of stuff I do and why I think chips are so interesting and amazing and important. So yeah, let's get started. So for my first, basically from preschool all the way to 8th grade, I was part of this private school called Challenger School. There's like many campuses throughout California and Utah. The school is heavily focused on academics. That's what they are really known for. And so, when I was there, of course, all of my students are, all of my peers are like, really brilliant and in a way, it's good, right? You're kind of surrounded by really smart people, but a lot of times too, if I could be honest, it was like sometimes demoralizing at times because these people are all so driven, and sometimes I honestly didn't have that same kind of drive. The one thing I did really well at was math. Social science and stuff was never really my thing, but that's basically something I always held on to. Like, okay, that's one subject that I really enjoyed a lot, and it's of course like the natural language of engineering and everything. So that was just something I just continue to enjoy. Yeah, this graph's just so like kind of like based on like national test results, like compared to like just Challenger school students and private school averages and national averages, just how the prowess of the kids there, and it continues to this day. So moving on from elementary school, middle school, like kind of like what Emma and Jacqueline already mentioned. For high school, I attended this school in San Jose called Valley Christian. It's a great school. I really enjoyed it. Of course, it's not. I'm not. Oops. Sorry. Go back. It's I wouldn't say it's like the most academically rigorous school. That's not what they're known for. I think they're more well-rounded in terms of like the athletics, the arts programs, and they have like a lot of different resources. Um, Basically, coming from Challenger to Valley, I wasn't like I didn't think of myself as like this really great student per se. So I was kind of afraid in my freshman year, like, oh, am I gonna adjust well to like this totally new school, different new environment, everything. So like in terms of like the classes I took, they were not like the most difficult, other than like the math. I took like honors algebra 2 or something like that. Um, but when I got through freshman year, it seemed pretty easy. I guess maybe Challenger prepared me really well for that. So I thought to myself, okay, maybe for sophomore year, let me load up a little bit more, take more honors and AP class, and that was kind of the trend throughout the rest of high school. And luckily, I did well. I got like straight A's and everything, but it wasn't without a lot of sacrifices in terms of like social life and stuff. I spent a lot of time just doing homework. I remember times honestly where it was like I would come home and be too tired from school, or be too tired from the night before staying up studying and everything. So I'd like fall asleep until like dinner time, and then eat dinner and study until like 4 a.m. and fall asleep and kind of continue all over again. But basically, like the thing that's going to kind of come up again and again is like for Challenger, it was kind of like you're basically told exactly what classes you are. You didn't really have any options, right? But I guess as you go further and further in life, like high school, things start to kind of open up. So I kind of got to try different things, like in terms of like choir and different kind of science classes and whatnot, right? Music classes, in addition to like the core, like math and social sciences and stuff. I did continue my interest in math, like was really involved with math club and stuff. And yeah, once I got to my senior year and college applications kind of rolled around, I'm personally like a homebody, so I didn't consider like I wanted to really travel far for college. So like when I applied, I basically only applied to all the local like CSUs and UCs. But I knew that I wanted to do something in like the electrical engineering and computer science or computer engineering realm, because I honestly didn't want to move away from Silicon Valley, and that was just my preference. So yeah, when it came, again for like the college application and stuff, I think Valley had like a really good like counseling, to like help you like write your essays and everything. So this theme that it's gonna come up again and again for like the upcoming slides too, is like the point I'm kind of trying to drive through is like wherever you are, it's kind of like make good use of your resources. Like for me, having those like working with some of the teachers that were also college advisors, it was just really helpful to get my application all set. Like this 17-year-old that doesn't really know what's in front of him, right? And kind of like what I touched upon before, it's like majority of people that may seem like successful and stuff, wherever they may be, like even middle school or high school, it's like I think they may be naturally smart, but there's always a lot of hard work that comes into it. Like I mentioned about all the studying, right? Um, so that's always there in the background. It's like for a majority of people, that's something you have to remember. It's not just like magic that things work out, right? And also like in terms of maybe for some of the attendees, you may be like younger students, and it may be like a lot of like your parents like trying to like either wanting you to be in this talk or like wanting you to get do well in school and whatnot, which is all good. Well, like I also want the same for my kids, but it's also like it's like the point of what I want people to also do is like take ownership of your education. It's not your parents' education, right? It's your own. So it's kind of like learn whatever you can wherever you are, and it will benefit you like in the long term. So yeah, moving on to college, like the college I wanted to get into was UC Berkeley, and luckily I did. But once it's like a top-notch university, especially like the engineering program is like kind of cutthroat. There was like I think only like 5% of freshmen got into that program very recently. It wasn't as hard back when I joined, but I think it's just getting harder and harder with like the same number of slots or less, and like more and more people applying, right? And really smart people applying. So once I was there, you take all the required like calculus, math, physics, CS, double E, like computer science, electrical engineering classes. And I'm surrounded by all these like really, really smart kids again, if not even worse. So I felt like it was like Challenger all over again, if not worse, right? So coming in, I honestly thought I would do computer science because that's like a much more popular route. But that didn't work out, honestly. It just wasn't for me. Like there's still a lot of like programming involved in chip design. It's just not the main focus. Like we're doing coding and stuff, but trying to manipulate objects like components on a chip, not just exclusively code, right? One thing I would say about Berkeley, it's not a bash. It's just I felt like the teaching there was a lot more theoretical versus practical. Like there's all these really, really smart professors doing research as opposed to maybe some like CSUs, like where they may teach you a lot more practical things for the workplace. So kind of like for me, like I had to do a lot of the practical teaching on my own. And through that, kind of like through internships and find like just working outside of school, I tried different things at school, but then outside of school, like an internship with like LSI Logic, which is now like a part of Avago and Broadcom. Like I found my love for chip design, and that's when I kind of started pursuing it more, right? So like my senior year, I was looking for jobs for like after graduation, and at the campus career center, there was like this listing for AMD, like advanced micro devices for like a new college grad. So I prepared hard and I got that job, and I was quite happy with that. So again, like I mentioned, like I'm going to bring up the same points about like intelligent and hard work, right? I felt like I was surrounded by all these smart kids, and I wasn't sure if they're like, it's just naturally everything comes easy to them, or they worked hard, or it's both. Probably it's both. That's what I would think. And like, in college, as opposed to high school, you're really a lot more on your own. Like I think high school, they'll still kind of hold your hand per se, try to make sure you get through. But college it's really up to you to make it through. It's not a guarantee, right? So getting through was not easy, but with a lot of hard work and dedication, it was doable. Yeah, so let me start shifting to like the work experience, right? So I was at AMD, my first job out of college, 2013, for 3.5 years or so. The first 2.5 years, I was on the CPU design team. So for those of you that don't know what a CPU is, it stands for like central processing unit. You can think of it as like a brain controlling a body. It sends signals to control the other parts of computers. So like when I was at AMD, the project at the time was Zen, the first generation Zen's processor. I think now they're like on the third or fourth generation or something. So once that design was complete, I moved to the GPU design team. So a GPU is like a graphics processing unit. Like the description there is like a processor that renders images and animations and graphics and displays them on for the computer screen. I think some of you may be like into video games and stuff, so GPUs play like a really big role there. And AMD is known. I think AMD like had acquired ATI a while ago, and that's the division under AMD that specializes in this, right? I think I was working on Vega 10 architecture back then. Now it's moved on to like Navi 10 and even beyond that. So like on the right is kind of showing a picture of like a Zen CPU and Vega GPU system put together, and what AMD calls like an APU, which is like accelerated processing unit. So it kind of just combines all the compute together. So it's kind of like a nice picture showing like the big things I worked on while I was there. Again, like being a new grad, and you're going to be handheld a little bit like by a manager, and you're going to have like a lot of resources made available to you. So it's kind of like they may ask you to get certain things done, but ultimately it's like you can go as far as you want in terms of like the resources available to you at companies at corporate level. Same thing about intelligence and hard work. Like you may be smart, but you can always learn a lot from other people. And it's one thing to learn it, but also doing it and doing it well is something you just have to get good at doing. And again, taking ownership of taking ownership of like your education, now of your work. That's very important in terms of you're ultimately responsible for getting your tasks done. It's kind of like, it's really important to make sure you follow through with like whatever you start, make sure you finish it. it doesn't look good if you like kind of just start something and like just linger and like end up someone else having to finish it for you. It's just kind of like a word of advice in terms of like mentality wise of like being successful overall. So yeah, so moving on, like after AMD, I moved to this small startup. Not many people may have known of it. It's called Flex Logics. So you may wonder like the name origin. I think it's kind of like flex meaning like flexible, and logic is meaning like logic. So it's kind of like saying flexible logic. What this company designed, is mainly like they call it FPGAs, which stands for field programmable gate array. So the concept there is like these computer chips can be reconfigured depending on the need. This is kind of like this picture of like DNA going into a chip. It's kind of like saying that it can be reconfigured and it can be changed basically. So I have a point here saying like typically FPGAs are bigger and slower than ASICs. So I guess I should probably talk a little bit about ASIC. So ASIC stands for like application specific integrated circuit. Kind of like what I was talking about when I was at AMD is like, so something like a CPU or a GPU is built for a very specific purpose, and only that purpose. It's not, I mean, it can be, it was designed for that purpose. I was going to kind of go into like how GPUs can be used for like cryptocurrency mining and stuff, where it wasn't like the original purpose. But nevertheless, the point is like whatever it can do, it's set to do that, as opposed to like an FPGA where you can actually change what it does. If you have like a really basic example, it could be like, I want my chip to add 2 numbers and give me the result. You can also reprogram that same FPGA to multiply 2 numbers and give you the result. But it's kind of like you can think of it that way, where it's just like, yeah, you can change it to whatever you need up to a certain limit. It has only so many resources and stuff, right? So this company was basically focusing on what they call embedded FPGAs. And that's as opposed to like a discrete FPGA where you just have an FPGA standalone without anything else. This means kind of like the bottom picture where it's like the embedded FPGA becomes part of a bigger system. So SoC, it actually stands for like system on chip. So it's one of the many features on this like system. So this system, it may not be kind of hard to see. It may have like a CPU, it may have some double data rate interface. I know it's not, that's beyond the scope of this, this talk, but it's kind of like saying it becomes part of this bigger ecosystem. And yeah, so I was here for like 15, like a little more than a year, like 15 months. It spanned like 3 calendar years. Being a startup, it's like a lot smaller than a corporate like AMD. So you get to do a lot more different things in a very small amount of time. So I'll talk a little bit more about like the day-to-day things I would do as the chip designer there. But yeah, after Flex Logics, I moved on to Tesla, where I currently am now. It's been almost 4 years. And so I joined so again, none of this is confidential. It's all already public information, right? So so there's this quote from Elon Musk. I think a lot of people know who Elon Musk is. He's our CEO, right? So on his Twitter, he had said like, Tesla is developing a neural network training computer called Dojo to process truly vast amounts of video data. So this is again kind of beyond the scope of this talk, but it's like the concept of like neural networks. It's like this computing system inspired by like the biological neural networks that constitute animal brains. So the idea is that for Tesla's self-driving software, self-driving system, of course, it's not fully self-driving yet, but the goal is to get there someday, right? So the idea is to train these brains, like these neural networks, so that they can recognize objects on the roads and eventually drive itself, right? So yeah, like the second point, like Tesla is handling an insane amount of video data from its fleet of over 1 million vehicles and growing, and it uses it to train its neural nets. Right now, we would train our neural nets on like just images fed from the car, like images of stoplights or stop signs, crosswalks, lane lines and stuff like that. But that's kind of like a two-dimensional view of the world. Like in real life, it's like three-dimensional or with time, right? So video is like a much more effective way to train. And I think originally we were doing like training based on, I want to say, oh, sorry, I want to say like we would train the neural nets based on like existing hardware, like GPUs, for example. But those GPUs, again, were not designed to do this specifically. At least that wasn't their original intent. And it's like it's not as efficient as we would like it to be. Like it's not as power efficient. It's not as fast. So that's where Elon wanted to have this project. So I kind of showed some pictures. This is from like Tesla's AI Day in August of 2021. Like this D1 chip is what I worked on. Kind of showed some of the specs. It's like 25 of these D1 square chips are combined to what they call like this compute plane. And that gets combined with like all this heat rejection and power control and direct current and this training tile module, which a lot of the challenges from here is like cooling these chips down because they're just so power intensive. It's just so much, they're just generating so much heat and it just needs to be maintained without burning the chips, right? And you kind of, the idea is like to combine all these training tiles, and this is a very simplistic view, just combine them all, put them in these cabinets, and all the video data will be sent here and used to train the neural nets. That's kind of like a very basic view of what the things we're working on. So yeah, that's basically like, yeah, again, the basic premise. And you guys can always watch the AI Day presentation on YouTube whenever you have time. So yeah, so like some of the things like I focus on in terms of like the chip design, just to give you more info, is like, so the main thing is called physical design. It's basically, there's like, I kind of broke down the different aspects of it. So there's this concept of floor planning where you have, for a chip, it can be broken down into many, many small pieces. If you guys see like floor plans of houses or whatever, not like you kind of break up a big box into a lot of smaller boxes, and you kind of divide and conquer, and you kind of assign individual owners for those blocks. And within those blocks, they have like a certain number of components you need to place. So, so there's like the concept of you place all these components like kind of tightly close together. And in order for them to talk to each other, there's this concept of routing. You have to connect them with like metal wires in between so that they can talk to each other. And the big premise of chip design is like this PPA acronym comes up, like power performance area. It's kind of like there's always a trade-off in terms of if you want to, let's say, increase the performance, you may need to burn more power and use more area. But it's kind of like if you use less power, you may get less performance. It's kind of those kinds of things, right? And of course, when you build these chips, there's a lot of rules in terms of like, so one thing is designing the chips, and then the other thing is getting them mass produced. You go to like a foundry like TSMC, like Taiwan Semiconductor Manufacturing Company, or like Samsung. So there's a lot of different rules based on like they call it like technology node, like the size of the components you're using. There's a lot of like these design rule checks you have to meet, among other things. And in the old days when chips were like I don't know, 50, 60 years ago, when they're just starting off, they're like really small back then, really basic. Now with like, hundreds of millions of components or billions of components, like it's not possible to do this by hand. So like for chip designers, we like for physical design especially, there's a lot of like computer aided design tools, CAD tools that we use, like from like Cadence and Synopsys, to help us along, because like I mentioned, it would be too crazy to do this by hand. You would never finish, and it'd be like so error prone. Yeah, so that's like some of the main things I do day to day. And there's other things like I did in the past. A lot of it happened at the FlexLogic startup. I won't go into too deep. I'll try not to like make people gloss over anything. It's just like some of the things other than physical design is like the step before physical design is like this concept of RTL design, like register transfer level design. It's kind of like that picture, that first picture on the top right, on the top. It's like defining, they basically code the way the chip is supposed to work in this like some different hardware description languages, HDL, for example, Verilog or VHDL. So I did some of that at FlexLogix, and yeah, it was like a good experience. And a lot of like we have to like read a lot of this code as physical designers to understand the intention behind like the blocks we're working on. And then there's also this concept of like design verification. So kind of parallel to like the RTL design, there's like you need to make sure that functionally, like for example, this piece of logic works the way it's supposed to work. So you would like stress all the inputs and make sure the outputs are as expected, for example. So did a little bit of that at Tesla too at first. That's actually a lot more software oriented because you can do a lot of things to stress the, like to make sure the chip works as it's supposed to, which is pretty interesting. And then there's like this concept of like post-to-look and bring up validation and characterization. So it's kind of like once you design a chip, you meet all the rules and you send it to the fab and it comes back to you after many months or so. You have to do some basic bring up, what they call is make sure like I kind of slowly turn on some of the knobs of the chip so that to make sure that it works. Like you kind of turn on just a little bit of power, a little bit of, kind of make it run really slow at first just to make sure it has life. And then once you're kind of sure of that, you can start cranking it up in terms of like run it at higher power or higher speed. Like that picture on the bottom right is kind of showing this concept of like voltage versus frequency. Kind of a funny name. It's called like Schmoo plot. So like the green is showing it's passing for a certain voltage and frequency or like a power and speed combination, and it's failing at a certain, for other points. So those are the kind of things you do for characterization and stuff. There's many more sub teams like I could go over, like performance modeling, design for test. There's just so many, like thermal, mechanical. I'm not going to talk about that here, but like there's just all these different subdivisions of like everything being important for the chip to work. And there could be like tens or hundreds of people on these teams, and some of these projects can take like months or years to complete. These teams are even, it's not like people are just taking their sweet time in terms of like getting, even if it takes years to complete, right? These teams are all like working in parallel, kind of handshaking and making sure everything's right up until the end. So, and like a lot of this may seem like over your head, I guess, or like, but and even like going back to like even grade school, it's like a lot of things take like just baby steps, just take it one step at a time, and it takes hard work and like determination to make sure things follow through. So it's not like it's impossible for anyone to really achieve this. It's totally achievable for if you guys are ever like interested to become like a chip designer someday, right? Yeah, so I thought I would like share a little bit about like where chip design is headed in the future. So this first bullet about like how using existing chips to design even more powerful chips. This has already been going on because like, those computer aided design, those CAD tools, they run a lot of you basically, when you run certain, you run the software to do some of like the jobs for the chip design. And those jobs have to be submitted to machines, and the compute has to be there to run. So you kind of use existing hardware to design this next generation hardware, for example, right? Google has, for example, taken it even a step further in terms of like using machine learning or like, artificial intelligence for chip designs. Again, it's kind of outside the scope of this, but the basic idea is like using software and running all the different like combinations and doing it efficiently compared to a human, and having it design the chip for you. And I think they had some studies where actually the Google designer, like the artificial intelligence was actually outdoing the humans. Not to say that humans are going to be like out of jobs, but it's kind of like goes back to like in the old days when humans used to like do all the design by hand and everything and manually. Now we have like this software that humans created to help design, right? And now it's kind of like humans design these artificial intelligence, machine learning models to help design. So it's kind of like the human just becomes that much more efficient, and the chips just become that much more powerful, and it just keeps compounding. That's what the trend I keep seeing Like this just seems like there's no end to like the possibilities here. I kind of touched upon like the EDA tools using artificial intelligence for chip design. Like I think like Cadence and Synopsys, these companies, I've used one of the Cadence tools like Cerebrus, to kind of like brain thing to give me some improvements for my chip. So I've already seen that firsthand, to like save some power and improve the performance and stuff. So like Meta, for example, it's like formerly known as Facebook. So for their metaverse, like whether or not you agree with whatever they're doing, Mark Zuckerberg, I think recently was saying like metaverse requires like enormous amount of compute power, like quintillions of operations per second, which is kind of like I can't even put that, like fathom that. I was trying to look. I think he calls it like a AI research supercluster. So he had like sent that out on Facebook. So I think this is like a trend, not just for Facebook, but even like I think Microsoft and Intel are also building these massive compute farms too, like Tesla also, right? And yeah, it's just like interesting, like software and hardware just continue to coexist and be intertwined. It's kind of like I was saying, like in school, like coding wasn't really my thing. Not that we don't code as chip designers, but the two are just so dependent on each other. Like software may be like quote unquote the more sexy field, but it's just like good software needs to run on good hardware, and good hardware needs good software. So the two just like they will continue to coexist, and be completely dependent on each other. Yeah, so like I'm getting towards the end of this talk. So like, why are computer chips so amazing? I kind of went over like some of the things that I think have made them, why I got into it in the first place and why I continue to just be so passionate about it. This concept of like transistors, like you can think of it as just like a component of the chip, right? There's like nowadays, like in the old days, it was like hundreds or thousands, tens of thousands. Now it's like hundreds of millions or billions and billions of these components. And it's hard to believe like in like this chip that you can hold in like your fingers, there's billions of these things. And even like to connect all of them together, there's like many metal layers. There's like 10 or 20 or 30 metal layers connecting them, and like and they are stacked in like a Z direction. So like the lower metals going up to the higher metals, and going back down and going up. And it's just crazy to me. Even though I've seen it every day, it's just the concept of it is amazing, packing it in such a small amount of area, right? And like there's this continued innovation and advancement. If you guys follow, like there's this concept of like Moore's law. Gordon Moore is like one of the founders of Intel. And it's kind of like the concept of you can continue to pack more and more transistors and components into chips and shrink them. It's like people say, oh, this trend is ending, but there's just been different ways that people have designed. Like it may have slowed down, but a lot of innovations come not just to like the technology, but like the architecture and like the things that the chips want to do, like they want chips to do and stuff. There's like this kind of hardware renaissance going on where chip design was like a big thing, I think, like more in like my parents' generation. And then software became much more like the thing to do. But now there's like all these companies trying to get into like high performance computing and everything. So it's like kind of back in, especially for like the AI, like the artificial intelligence workloads, like they need lots of compute underneath. And like in terms of like the fabrication steps, so fabrication is kind of like when you manufacture the chip, like you get like metal layers, and you like kind of you actually manufacture the chip. There's like hundreds and hundreds of steps if you look it up in terms of like oxidation, poly, like all these in like filling in the metal vias and stuff like that. It's just like amazing how they do this, and they're able to get like yield in terms of like a lot of chips that actually work. It's not always 100% yield. Sometimes the chips just don't work. These steps are not perfect, right? But they're pretty close to perfect, like in terms of getting high yield, right? There's this like stat about like 300 billion chips sold in 2019. That's like 40 chips per person, approximately on the globe, right? So that's like, and that's 2019. I'm sure there's more like in these more recent years, right? So it's just like silicon is everywhere. It's like readily available on this planet, and they've been built into these computing chips that we use every day in our daily lives. And this concept of like 3 nanometer technology. So like the size of the components and transistors, the gate size is like 3 nanometers, for example, one of the more recent technologies. And it's shrinking even more. And there's more different ways of they're coming up with new technologies to like um, to be able to pack more and more components in. Of course, with all this, there's all this power. You need to deal with all the power consumption and stuff. So it's just like it's amazing to me, like how it just keeps going and going. And this is like my last slide to conclude. It's like, so like, why are they so important, right? So I think people may or may not realize how they power like everything in our daily lives. Like, for example, like in computing, like whatever device you're watching this webinar on, like your laptop or your phone, tablet, whatever, like it's all being powered by a chip. In terms of like telecommunication, they have like your satellites, when you make a phone call, the signal goes to a satellite in space and it gets sent back down to whoever's receiving your call. Your Wi-Fi, your Bluetooth antennas, your wireless router, all of those have chips in them. Household appliances like your smart fridge, whatever, your like AC control at home, your Ring doorbell, Nest thermostat, whatnot. Those are all powered by chips also. And like banking, like olden days, if people only dealt with like paper money, that just seems like prone to like a lot of risk in terms of like whatever, what if the bank burns down or whatnot, right? So everything is like electronic and also secured by security in terms of like for banking, for example, there's like a lot of security chips to make sure everything's encrypted. All your data is stored on the cloud, make sure it's secure. Like healthcare, let's say you have a pacemaker in your heart, right? That has a chip inside. You go to like a doctor, you get your blood pressure, your weight taken. Those all like typically have gone digital, and there's still manual things, but like digital can also be accurate too. Among other things, like even like just storing all your data and stuff for healthcare. In general, it's like all on computing platforms. Like transportation, of course, Tesla, like the Tesla cars themselves have like a lot of computers in them, but not just Tesla. Like all cars have silicon in them, and there's like this whole concept of like chip shortage, and it's hurting a lot of people, like and automakers and stuff. Like your airplanes all have GPS and everything. They also have chips inside, and buses and everything. Like your like stoplight systems are all controlled by chips too, by sensing the weight of the car that's there at the stoplight and whatnot, right? Like manufacturing, like all the electronics and stuff you'll have to buy, like PS5s, whatever's modern now, like game consoles, iPhones, whatever. Those are all controlled by like robots or like automation that has silicon in it too. So yeah, and like I kind of touched upon it already about like how software and hardware they're just so dependent on each other, right? Software won't work without hardware to run on, and yeah, hardware is not meaningful without software either. So it's kind of like, yeah, well, they're so important, and they're these chips are everywhere in our lives, and I don't see any I don't see that changing anytime soon. So yeah, with that, thanks for attending this webinar, and I'll open it up if anyone has any questions for me.
All right, awesome. That was a great informative webinar. I know I learned a lot. Hopefully everybody in the audience did as well. Yeah, so audience members, if you have any questions, just feel free to leave them in the chat, or you can just like unmute and ask them out loud. I did get a few private messages during the webinar, so I guess I can go ahead and start with those. So the first one, let me scroll up and find it. So how would you compare your experience working for a startup versus a big company like Tesla?
Oh, good question. Yeah, I touched upon it a little bit. Like the startup, it's like a different mentality in terms of like you kind of have to do whatever it takes to survive. Honestly, like we have, at least for like this startup I worked with, the manager was very open in terms of like the money runway we had. There's like, okay, this is how much money you have left, and we need to make sure we don't run out and make sure we start making money and get the contract and stuff. So it's like you get to see the business side a lot more, I would say, compared to like AMD and Tesla. I'll talk about AMD first. It's like AMD is pretty big, and I was kind of shielded from a lot of the things, the business side. In terms of like the technical work, because it's such a big team, a lot of infrastructure was already set up. So kind of handheld a little bit in sense like, oh, there's a lot of people looking out for my success and like keeping track of like how I'm doing and stuff. And at the startup, it's like, no, you're on your own basically. Like I was employee number 12 at the time. And I think now they're like at 50 or 60 employees. They're doing well. But yeah, you get to put on a lot of different hats per se. Like I mentioned, like my main focus is like physical design, like the place and route and stuff. But like the other aspects, they needed people to work on that too. So, and I had interest, so like I got to do those things. And like I wouldn't have gotten to do those things at AMD. It would have just been a lot harder to do that and get guidance. Whereas more like at a startup, you're kind of free to like you just have to explore. And this interesting part about Tesla, it's like my team is kind of like in a kind of startup mode where it's like it's pretty open too in terms of the work you can do. It's just that we have a lot more funding compared to a startup. So it's kind of like the best of both worlds. So hope that kind of sheds light on that topic.
Yeah, and kind of a follow-up, would you say the work environment is more stressful, like I guess hustle culture at a startup versus a big company, or is it like relatively the same amount of like stress and workload?
For me, it was a lot more stressful. To be honest, I felt like a lot hinged on me at the startup compared to like the big company. Not to say that there isn't stress either. But yeah, it was pretty intense at the startup. Like they had set that expectation up front. Like you're gonna have to work a lot more than you're used to, and it's just the way we have to operate in order to like keep the lights on, for example. So figuratively. So
Yeah, awesome. Okay, and moving on to our next question, from another fellow high school student. Tips for high school students interested in entering the industry of chip design, like classes, programs, etc.
okay. Yeah, I guess if it's like I think I know Valley Christian, like if it's Valley Christian or any high school will have like of course the math and the science classes are going to be important just to get a I wouldn't say you have to be like the best at it, of course. Hopefully you enjoy it. It's not like I use a lot of like complex math and physics every day. It's kind of like for chip design, it's like this sector of physics where it's like a circuit design of like it's a very narrow view. It's like a specified view. So it's kind of like if you enjoyed that kind of problem solving, that's applicable for like a lot of things, not just chip design. Like if it's more specific for chip design and like this field, it's like if your high school has like program or like if there's any sort of like programming classes like introduction to Java or whatever, C++, whatever the hot languages, Ruby or Python, or like AP computer science, or like if there's like an even like extracurricular programs, like I think like Code Ninjas, for example, those would be good to get just an introduction in whether or not you like it or not. Like I personally didn't love like just hardcore coding, but there is like this concept of scripting and stuff where you do have to like write some basic code. It's not that complicated to like gather a lot of data efficiently, like from all the like different runs I was saying. If that kind of makes sense. So
Yeah, definitely. And kind of a follow-up, another direct message, is physics more important for chip design? And is there an extra class we need to take starting from high school to get into the profession?
physics is important because it's like if you get into like the really nitty-gritty details of like device physics and how electrons move, like the very heart of the chip. Like yeah, it's important, but like let's say if, when I applied to schools, you didn't have to like have like a certain class signed up, like checked off your list to be able to get into the program. They kind of look into like holistically, like how you, I think like they care mostly about like the rigor, I think, of your academic program and how you did, of course. I think they care more so obviously about like, I mean, I mentioned like my freshman year wasn't that heavy, but I tried to like make up for it in sophomore and junior years and senior years, and Berkeley like that, for example. Like the senior year is like when you apply. So it's kind of like the first 3 years, they're gonna take that, it's gonna have more weight compared to like your work. Like you're gonna apply in like in like November and stuff for like for those schools and stuff. So they may not even see your how you did your senior year, but like as long as you had like a good class schedule and then you did well, and I think there's cases where they can rescind your acceptance, right? So you just have to make sure you do well even once you get in. Does that
Yeah.
make sense?
Yeah, definitely makes sense.
Yeah.
Okay, let me scroll back up. There's a lot of questions in the chat. Okay, so is chip design a easy profession to transfer into? For example, if I was interested in business, how hard would it be to change my major or profession to chip design later on?
Yeah, I guess it depends on like the school and like the amount of overlap in terms of like the classes you need to take. It's like for like chip design, it's like it's part of the broad electrical engineering field, electrical and computer engineering. But if it's like from business, for example, you may have to like take a lot of you may have like maybe one or two overlaps in terms of like general electives, but like the required classes for like math, like calculus, linear algebra, discrete math, the physics, like the computer science, the programming classes, and like the you may have to just like kind of start over, which also like is not it's not the end of the world, I would say, if it's something you're like super interested in. Um, it depends on like your tolerance in terms of like if you can keep the business program up, for example, and like start taking extra classes on the side, or like just even not even like going far as to like taking the classes, or like just reading watching some videos and stuff to see if like there's a lot of like self-learning material nowadays, right? You can learn a lot of things on your own. um I would say like if it really does pique your interest, then you may have to like start over, and that's okay too, if it's really what you're like your calling.
All right, cool. Going to next question. How much scripting do you use in your physical design job, and what language do you use for scripting?
Scripting is there a little bit, like I don't know what percentage, like good question, maybe like 15-20%. Kind of like, if people don't know what it means, like I guess I use like Python or Perl scripting. It's kind of like you have all this like it's like these coding languages to help you like gather data from all the like the if you guys have ever used like Unix language, where you like all your data is stored in like, I guess if I go back to like if you're like on a Windows or a Mac, for example, computer, you have like all your files in like different folder structures. So like in like chip design, we use like Unix and stuff, and it's like a instead of a graphical base, it's like a text base where you can like search things, and like for all like the existing reports, you can use the scripts to parse them, and it helps to do that and save time, as opposed to like opening the file and searching manually for like this very specific thing you're looking for. So that's where it kind of comes in handy, but it's not like my main job still. Um,
All right. All right. And kind of another question on a similar topic. As a chip designer, how proficient do you have to be in coding?
I think you have to have like the basic concepts down, like recursion, like that's like a definitely must, but it's not like super complex. A lot of the EDA tools, like they have like very specific coding for that specific tool. And then like let's say for like a lot of this physical design, it's the language is called like TCL, tool command language. It's pronounced tickle. It's kind of funny name. Um, and there's always a lot of, you can always look it up online and they'll kind of go through a lot of examples, like setting this variable, setting this list, manipulating, like searching this list, sorting the list, like doing recursion on this list, or whatever the data structure is, like like an array or whatnot. So I would say basic proficiency is like good enough, at least for me. I've gotten by so far with like not crazy hardcore coding, but if you're really good at it, it does actually help to get the job done even better. So it can go as far as you want it to go.
All right. And last question, for the sake of time, what steps go into the design of an IC?
Oh, there's like a lot of like different steps, but I can go into like what I can think of like in terms of yeah, what I'm familiar with at least. So there's like basically like you have a figurative or literal blank paper, right? And you tell yourself like, well, if you wanted to start from scratch, it's like, okay, so what do we want the chip to do? Like what we want it to do? This is what like they call computer architects. They kind of come up with, okay, this is what we want it to do. And then they talk with like a lot with like the RTL, like the hardware description, like the HDL, like the coders, basically they code it into like a hardware language, coding language, like RTL, like Verilog. And they will implement that. And then that has to be like kind of like the things I talked about, like the different tasks. That has to be functionally verified in terms like through the design verification. And that goes on in parallel. And then that code also gets handed off to the people like me, like physical designers. So there's this concept of like synthesis where the RTL code is translated into the components that we're going to do like the placement and routing stuff. And that's a CAD tool. That's like computer aided design. It's not like we're going to manually translate it. So there's the companies have like Cadence and Synopsys have mastered that art basically. So that basically gets converted to like this, they call it netlist, where it has all the components and like the connections in between them. And then like my job is to place and route it, like make sure it kind of like what I talked about. It has to meet all the manufacturing rules. It has to fit. It has to be able to connect to each other everywhere. It has to be a reasonable power consumption. Once all those checks are met and everything, then they have this concept of like GDS out. Like, I forgot what it stands for, but it's kind of like they call it tape out. In the olden days, like you would literally have like this tape paper thing that it will be printed out and sent to like the manufacturer. Now we send it like a graphical data system. That's what I think GDS stands for. That gets sent to like TSMC or Samsung, and they manufacture it, and then it comes back to us, and then it gets like packaged, and then they do like the post silicon like validation and characterization and stuff, and then that's like some of the steps. There's a lot of things like kind of left out, like performance modeling, DFT, like design for tests, thermal mechanical model, stuff like that. That's kind of like my basic understanding of like, and the main teams I've like interacted with, if that helps.
Okay, great. And I think that was the last question because we don't want to go on for too long. So if anybody else has any questions, you can be sure to send them to us at the Young Expressionist. We'll be sending out a follow-up email to all the attendees here today, probably around tomorrow, also with the recording of this webinar in case you have friends who didn't get to attend, but they still want to watch it. So if you have any questions, just be sure to reply to that email and we'll probably send them directly to Anton and he'll be happy to answer them for you. But other than that, we're just going to go ahead and wrap up. So a big thank you to our guest speaker. It was a really great talk and I know everybody enjoyed it a lot. And also a thank you for the audience for just being here. So again, if you have questions, definitely let us know. But other than that, we'll see you next time.
Thank you, everyone.
Thank you.